Oh my God, so this is Bison. Incredible. Do you know, I actually wanted to be a maths teacher when I trained to teach, and then the people at the GFE told me you can have foreign degrees or you can have degrees that are not like outright in the subject, but not both. But I've got massive maths envy. Particularly, there it is, like this one. There's a whole bunch of I think it's in further maths. You can pick like a module, and one of them is basically decision maths, which is discrete mathematics, which is the all overlap of the AQA. It's got a lot of it, like graphs and trees. They're kind of well done in OCR. I mean, I think I've made it clear what I thought about OCR. I'm surprised this is not my thing. I can't yet. My chemistry days are over. Botany though, wink. Right, yeah, okay, back on track. Let's have a look at what we want to be doing today. So what do we want to, like, yeah, if you want some topics, give me a shout in the chat. Yeah, like, point me to past papers, questions in the chat. Make that massive. For the people like coming in, I see there's like you can join the channel and there's like a $3.99 a month, $22.99 a month now. I'm not, you know, I've got like a bag jar underneath, but otherwise I'm not monetizing, I'm not putting ads on this stuff, I'm not doing that full time, I'm just doing this at the summer. Oh wow, okay, so they're putting the maths, well I was wondering whether, because like a lot of, you know, you see a lot of maths teachers, because there's obviously a shortage of all teachers, but like particularly STEM teachers, and within STEM used to be, before I like shafted all of the jobs, used to be a shortage in computer science, so there's a lot of, and especially you know, the curricula, the syllabus is like from 2015, so given the typical career length, there's a lot of computer science that's being taught by physics teacher or maths teacher. Teachers, and I was wondering whether you were kind of like, you know, Bison because you were also taking math or not. And yeah, it's I'm not super extensively familiar with the calendar. Right, A level computer science. I don't know. Actually, I'm gonna, rather than go by past papers, if I do computer science revision, because they're gonna break it down by paper. Yeah, A level paper 2, data representation, computer system, organization, and architecture. Consequences of use, OMG, this is where we get ethics, law, and networking, database, big data. Functional programming, yes, we do have functional programming. Oh yes, I love functional. Sadly, we don't go deep enough in functional programming, but hit me up for some more of this. So we could do it by topic. I think this is where we have like actual, yeah, internal hardware. We did a trace of the assembly. It's a nightmare. It scares everyone every year. What kind of like sticky bit are we going to have then, like in terms of like big questions? Maybe a database. Okay, let's have a look. Let's have a look at functional, because you never know, right? I mean, like it doesn't hurt to. Topic 7 is a brain twister. Which one's topic 7? Okay, 12. That's not that. Topic 7. Computer organization architecture. There's a stream yesterday where we did the. I mean, this like, okay, let's look at how this is assessed, right? Because this is pretty good. The questions by topic on PMT, because for each, not just spec but sub spec, you can get yourself. Let's have those are the latest. Now they like a lot of the questions overlap, so there'll be in several things and so on. This is mostly stuff you need to learn with flashcards, and you've got your like laser printer and your barcode scanner, like a couple of devices to know, your storage. But and then you've got all of your registers, kind of like internal hardware, buses, knowing what happened, knowing the fetch, decode, execute cycle, store program concepts, von Neumann architecture. Topic 7, we are in topic 7, discover store program. We've just literally just like, okay, fine, this is from another one. This, yes, sometimes the same question comes up in several years, so it's like, ooh, hello. Okay, so this is in this section because it hits, like it will hit the lowest level, but this will also be in wherever the, I mean, the, you know, where am I? Let's go back here. I think this is the helpful one, right? Like you've got things like the, is it, I don't even know where that is. The, like translators and compilers and high level and low level language. Yeah, this is one, types of program translators, which you can get yourself in here. But because at the very, very bottom, you will go from the high to the low, and the lowest level, this is kind of put in this thing, like the machine code instruction carry the program fetch and execute it from the processor for main memory, right? So this is where like you'll hit the program counter and so on. Translation, the compiler and interpreter ultimately will turn it into machine code. Translation is necessary because we could have like write high-level code that is closer to our language, but the computers needs it in zeros and ones. The difference between a compiler and interpreter will translate the program. One is line by line, the other is kind of done all in one bulk and then linked with external libraries. There's pros and cons, faster, slower. D-type flip-flop, that would be in Boolean. I mean, is it in there as well? So which topic has the D-type flip-flop? I gotta say, all of that bit, the Boolean wiring, that wasn't taught by me. It's taught by my boss, and I'm not super, like we've seen one, there was the flip-flop is the kind of the one that stores the sample and hold. You need to know your half adder and full adder. Those will be in organization architecture. Logic gates, yeah, here we go, logic gates in Boolean algebra. Ooh, I am excited. Okay, truth table, that's fair enough. The Boolean question, only if they're both one, or input P is 1 and input P is 0. So it's A and B, or C and not B. There we go, like wiring in it, so A and B. Oh, they've even given you the gates, that's really kind of too easy. Hello, is this a D-type flip-flop? I don't even know how D-type flip-flop works. Well, we might look at D. Logic gates advanced, this is the most extensive. Do we not have a table of content in this one? That's an adder, that's a half adder, yeah, and then the full adder, you can pair them until you get the carry in, there's three, so this doesn't, it's not really done super well, but like you can tell there's the shape of like, you can do, this way is called half adder, you put two half adders together and plug them into a certain way, because that's the input of this is a one half adder, that is like chuck into another, with an OR, because the carry is getting an OR, and then you get like both carry bits and then you kind of OR them. This is something you kind of need to learn or re-figure out from the truth table, because you know your Boolean adding. No, those flip-flops do exist. It's like, it's completely, this is how you sample. So in your representation of sound, right, you get like an analog sound wave that's kind of a, electric current that's varying into a circuit, and in order to digitize this, you need to sample it. And this kind of D-type flip-flop is the one that's going to get, so it's not doing zeros and ones, it's doing the actual like precise level. But your D-type flip-flops is how you store bits, basically in RAM and flashed ROM and flash storage. Is like you need to sample it, and to figure out the one you kind of sample and hold. So there's something that will hold the current voltage at the level it was every time you send it a pulse, and that allows you to turn your nice smooth wave into a discrete stepped wave. Edge triggered D-type flip-flop. Oh, so you don't know the thing, right? Two inputs, one for data, another for the clock. One output always at the value of the stored bit, and alternate 0 and 1 set frequency. And every time there's a rising edge or change in the clock signal. With each change in the clock signal, I wouldn't super sure. And then you can build a shift register for it. That's not like super detailed. Let's have a look at what we got here. There's some kind of random circuit. So far so thing. Fair enough. So converting between truth tables, your gate diagram and the actual expressions is easy. I am French, M. Annie. I'm actually Monsieur Bérard. There should be an acute accent on my name, but those are tricky to get on some keyboards. 2012, following logic gates. I mean, I don't know if this is likely to figure out. I reckon that, like, I hate to point you towards the hegemony, but Craig and Dave is bound to have a good video in the D-type flip-flop. You need to figure out like which minute, or like which 3 minutes in the 20-minute video, once you know which video it is, but like that's probably going to be well explained. Hello. The value at m, yes, is 1 and not c. And so that's 1 because that's going to be 1. No, that's just, sorry, that's just not c because 1 is, you know, in an and is neutral. And XOR, I want to say, not c. And it becomes not, it's basically, that becomes not c, weirdly, I think, right? Because if it's 1, if you could think of the truth table here, but like this ends up becoming C, and then completeness a missing cell. Oh, hello. Wow. We get the 2's complement with just this. I like this. This is kind of pretty cool. Oh yeah, that makes sense, right? Because where are they knotted? Yeah, they all fed into a knot, because 2's complement, as you know, you flip all the bits, which is why it all starts with a knot, and then you add 1. And so like this is done by with half adders, because we know we don't come in there with a carry bit, because that would be the lowest one, and then the carry bit then will carry into the sum of. We don't need to add, because it's with 0, 0, 0, 0, 1. So the only one, put it 1 and cascade the carry bit all the way here, and you take the 2's complement. Who would win the fight, you and Craig and Dave? I mean, Craig and Dave is like the what is it's the sort of hegemonic massive corporation. They have their own conference. Zigzag is Craig and Dave. Smart Revised Online is Craig and Dave. There's a whole bunch of sub-runs, and they seem to control computing education. So I'm not gonna speak ill of Craig and Dave, right? Because you know, they seem to employ a lot of people that have my profile. So, you know, when I get that, and it's actually Mr. Hillard and Mr. Sargent to you. I have a book by Craig and Dave that's literally in their actual names. Yeah, look at this. This doesn't look like Craig and Dave stuff. This is like really, really good. And this is where you see that I throw a lot of shade on OCR, but in fairness, as far as all of the algos that you have to know, they're all in there. The problem is that that's at the price of things like you know, reverse notation or whatever. And so this is by Hilliard and Sargent, which sorry, I need to kind of like check and see what's going on here. Yeah, which are Craig C and D Hilliard and C Sargent. That's your Craig and your Dave. All right, I'm really bored. I'm not sure I want to do that. Okay, so logic gates. I don't know. Do you want me to draw one? Hello. Yes. Okay. The general purpose of a D-type flip-flop is to store what comes into the input and store it whenever it receives, and whenever it receives a clock signal, store it in, and then return, you know, whatever that value of that storage bit. This is effectively how you can do memory. This is how you could delay individual bits coming in, because you can hold it until you get a thing, and because everything, this is shift registers as well, because like you can hold it, put it into the next one, and this is how you would do bitwise shift. But the purpose, anything where you need to, anything like your adders allows you to add things like from one bit to the other. The D-type flip-flop, because of that clock thing, allows you to hold it across through time. And once you've got this, like, you know, like you put a lot of it together, you've got memory, but then also using signal processing for delay effect. One input is a data signal. Then one other input is flip-flop. What is useful? This is the clock that will give the signal to the flip-flop to sample the data signal and hold it and have its output be its value until next such time as the clock signal changes. Are we still in the same one for this? They're changing this looks like a, you know, actual exam papers, and this is kind of a bit of a mix. Right, that's the D-type flip-flop question. I mean, it's notable, right, that like across, this is 5 years worth of this area of the specification. Yeah. We love these. So, I mean, I don't know, like, don't panic about this, but you figure out, like, what's the ends and the or. So I would probably, like, go. It's weird because I would feel more comfortable, like, going for the Boolean expression, because then from the Boolean expression I can draw the gate in one go without having to kind of refigure it out, or kind of, like, laying them out not the right way, and then you have to do, like, little bridges in your wires. This is easy. Anything else before 5.4 in 2020 paper? Yes. All right. Thank you. We are like an actual question, because an area is a little bit much. So at well, not let me load it up. Papers. Class papers of computer science from the AQA paper 2. 2020 5.4. It is a, I can't control F because this is not, those are not 3 characters, there's like a box with the, oh hello, yeah, that one? A LAN in Belgium. Belgium. Okay, let's do this one. So let me make a note of the time at 15:25, call it. We are doing 2020 Q5, and that's LAN, like some networking. Okay, figure 5 shows a computer A, which is located on a LAN in the UK. It is connected via the internet to an email server, computer B, which is located on a LAN in Belgium, in an address, and the public IP address, Fair enough so far. Isn't that like 1929? Well, whatever. I don't know. Yeah, my boss taught the networks as well, and like because that's not kind of like MAPC or signal electronics. So yeah, I don't really care. Like the DHCP is the thing that you come up and it assigns, like, you know, it recognizes MAC addresses and assign IP addresses automatically, which makes, I suppose, adding and removing devices from the network much smoother because you're less likely to have conflicts, and they don't. But the trade-off of this, that we just want one advantage. The disadvantage is that your random like little computer can't be guaranteed to always have the same IP address, but that's fine because it's on a subnet anyway. That's my punt. Let's maybe have a look at the mark scheme though, which is above. Okay, page down, 5.5. Reduce the needs for expect knowledge configuring a host, and the requirement to manually assign an address, automatic assignment of IP addresses, which reduces the time. Well, there's a lot of way of getting that mark. Reduces the time required to configure, avoids error. Not enough avoid errors without example. So that's kind of forgiving mark scheme in that there's many ways of, in fairness, one advantage, there's more than one, so they give you all of the one. Although they're all kind of interconnected, you can see that. Yeah, Canid BTW7923 says, I did so bad in paper 1, I need paper 2 to clutch bad. I feel like, yeah, good luck. Because this is much more learning stuff, well, kind of on the thing. Many other computers, so that's, let's see, so 2.3 have the same IP address. I explained how 2 more computers can get the same IP address and still communicate with each other. I don't know. There's some kind of address translation so that from the outside they appear to have like a single IP address, but really on the subnet, like the local subnet is how it's called, but like to the rest of the world it has a different IP address, a public IP address. I might want to have a look at the mark scheme then. Yeah, computers have a private non-routable IP address, and that you can't route, like, yeah, that's why this 19.2.168 felt like a little bit local. It's a private non-routable IP. The computers can have the same IP address if they're on different networks. So like behind the Belgian networks, like we all have a 192.168 subnet, and then you get, that's the one, then that. The thing that, like, if you're gaming on console, they're always going to be giving you stuff around, like, we translate the kind of private internal addresses to this. How does it know that the packet addressed to the external IP is meant to get to that computer or that other one? It's unclear. But I guess it's not in this section of the specification, probably not. Okay, router A3, so we're still on the network A, that's the UK network. Router A3 has a firewall to protect the computer. And you check 4 different ways. Oh, bloody hell. Like filter out, prevent requests going out to certain sites, prevent packets going into certain sites, blocking ports. So like you get something by IP. Ultimately, all of your networking is like, you know, what kind of like addresses, like back and forth, but then within that address, you get a whole bunch of ports because you're kind of directing traffic for different applications and services to different ports. And it's a matter of like, do you block where you can talk to, as well as do you block like out of the things you can talk to, like what ports are allowed. And I guess the fourth way might protect them via like logging, so they can be, that's a lot of ways. So you can track what's been going on. Block, allow traffic, specific port block, IP addresses. So certain types of packets, yes, that's right. The thing is that ping, technically everyone relies on ping, but ping is not like necessary, right? You don't have to implement it. Like it's kind of, there's no, you're not really blocking ping as much as you're not implementing it. Like your local laptop has got no reason to respond to ping, and I don't think it does. Firewall maintains information about current connections and only allows packets relevant to these connections through. Well, oh yeah, I guess, right? Because, I mean, stateful inspection, not enough. I wouldn't have known about that. I guess the proxy server, well, yeah, because it has to go, stops computer and directly addressing devices on the LAN. Identify unusual, yeah, so the logging, that kind of thing, right? Kind of, this is like, all right, why are you suddenly sending all of those things? And rules, well, I guess this is kind of a little bit of the rules about all those. But I would have had, yeah, there's 1, 2, they list 1, 2, 3, 4, 5, 6, 7, 6, 7, 8. No, that's 7, just 7. Oh, and then as an exclusive to, kind of thing, inspection of the packet header, because that corresponds to like the type of packet, the port, and the IP address, that's fair enough. But like, why like collapse it into one mark when, yeah, you can't have it in addition to that, but you can have all three. Yeah. That, so like there's like 7 or 8 depending on how you count ways of getting the 4, so it's kind of, it's scoped, you get some scope, but like you need to at least know some, and that was that. Yes, there's the 12 marker. Okay, computer A, so that's the thing. I check some errors. Computer data subnet mask across the line, a packet must be sent via the internet. Okay. Okay, so first they want to know like why, this is kind of connects to their questions, like how do we know, how do we immediately, as the packet just comes out, is it on the network or not, and like what's a subnet mask? So masking means you're kind of like really interested in part of the data, and so you're I think masking out, you're just kind of like disregarding what's at the bottom, and you're looking at the first two, and because the address of computer B is, what was it? They've given us like 141, 134, and so on. That doesn't match the subnet mask. So this is the mask. Anything 0, you let them through. It's kind of an OR, if you will. I mean, like you can imagine that in binary. And that's the mask. And because like meaning it's going to convert this address, put the mask on, and it gets only the first two. Notice that the first two are not like a subnet, a local subnet, therefore it needs to go out the wider internet. And then the little packet gets on its merry way. What's going to happen, the packet is routed over the TCP IP protocol, so it goes from node to node, and like the TCP itself, I don't know how much you want to get into the TCP protocol on this one, but TCP will send until it gets an acknowledgement and retry if it doesn't, but like back off and so on. The packet can be routed by sort of arbitrary destination because like routers will take their own decisions. The checksum, that's quite important. What will happen is like for the data content of the packet, you run some kind of hashing operation, right? That kind of like is a quick function that that collapses like a large possible offset onto a much smaller one, but also has kind of, if the starting points are close together, the endpoints are unlikely to be close together. So that reduces the collision. And then the receiving computer can re-perform the same operation and check that the two sums match, and that's why you use a checksum. Time to live, it's, I don't know why you're asking time to live, because time to live for me is something about DNS, right? It's kind of like about how quickly you propagate something, but let's have a look at the sharks meme. Okay, so the line of reasoning has been produced. So this is interesting because you can't just like tick off things. It's about like your ability to, because you've got different determining if online. So this is interesting because of course, yeah, I'm still tutoring in OCR, and OCR is paper 2 as well. Their 12 marker are not like, okay, 3 different bit and then it's knowledge on each of these. Their 12 marker, you've got like maybe 3-4 points for the knowledge, and then it's like application and critique or contextualization. It's kind of different layers of depth of understanding, so you'll want to kind of apply it. But here's a more of a technical answer. So the end application, the end masking, the result is the network, right? You only take the first two, and it's the subnet if they're different. That's a lot of point for this. Subnets must use the IP address system to compute some network subnet. The hierarchical organization, I didn't say hierarchical. National, I don't know about this, I thought it was peer-to-peer. They not determine that start, that they did that, kind of make it a pass from router to router, yeah, but not enough. They change as a result, whatever, repackaging of packets to different protocol. I did not know that, yeah, possible. And then the network ID address at this router table criteria, next hop. Not seeing time to live. Source and destination MAC address changed at each router. Yes, because you just only go looking from this device to that device. Oh yeah, okay. GTL in the context of IP protocol is the long the packet gets destroyed if it still hasn't got to this destination. Yeah, because otherwise they'll be clocked. Hey, there it is. Router decrementing time to live of packet. So that's to ensure that your network isn't full of like completely lost packets and chocked by it. Source and destination MAC address change the router, IP address of computer, right to A3, right? Because we don't know it's another one, we just go to the and then on the way back network address translation. And the checksum, that's a hash mod to limit magnitude of checksum, right? You can take it to a specific number of bits. Append it to the packet data, you recalculate it, you compare them, and if they match, if they differ, there's an error and good level. Yeah, so this is really about, I'm about to tie them together. Especially since those are really three separate mini essays, because they kind of like, there's not much crossover there's zero crossover into one another. Maybe you could link like come back the NAT to how you get back to the LAN a little bit, but like that's tenuous here. Okay, yeah, I would say M Annie in the chat, it says pretty difficult 12 marker in my opinion. Let's compare it with another then. Can anyone check me 2021 Q11? Yes, so let me load it up first. Okay, I'm closing 2020, born of this. 2021 QP 2021 mark scheme. And then thank you, Eden Mullet. Interesting. Eden Mullet. Eden party at no, business at the front party at oh, hello. Sorry, I just saw somewhere. Yes, you gotta love this stuff. I'm glad, yeah, okay. Well, I'm glad we're not doing this one. We're doing Q11, so that's dodge the bullet there. Yeah, this is your, sorry, the additional text. Q11, no, again, come on. Oh, you mean compared to that one? Like there's a 6, there's no 12 in there. Is there a 12? No. I've like blown past 11. Yeah, suppose that's kind of a better way of distributing this one. It looks very, very similar. Actually, this is easier. But remember, like, neither 2020 nor 2021, because you'd think, well, 2020 was so hard. Because 2020 was never sad. That's why they kind of like put something that very similar into that one. And 2021, it turns out, was never sad as well, because it was COVID times. So I'm not sure I'm fancy particularly doing this one, but let's... ooh. I have never heard, I have never seen those letters. This is annoying because this is a bit of a niche protocol just for kind of wireless stuff. This is like the lower level of the Wi-Fi I'm getting. I didn't even know that was on the specification. As I said, like this is not a bit of the spec I teach. Should we just go back? Don't teach the gates either, but let's have a look at that one because that just scared me a little bit. Okay, exciting things. So Fin client, you're the Fin client. Figure 1 shows a circuit with inputs x0 to x2 and inputs q0 to q7. Yeah, I think you guys need to go and get revising. I might, unless there's more questions, I can't. Can I just show you like just the thing about? No, let's see if I can find a functional question. No, not that. This one, okay. We've got 3 outputs and 8, 3 inputs, 8 outputs. A Boolean expression for Q1 is equal to not X1 and not Q what? Q1? Or is that just a bunch of adders again? Are they kind of having us on? Q1 is equal to not X1 and not X2, and the rest is ended with not X0. Are they all the same? This is very stupid. Oh no, 1, 2, 3. Oh, it's got it in the not sometimes. Okay, interesting. All right. So we've got like not. So 0, 0, 0, 0, 0, 0, 1, right? 0, 1, 0. 0, 1, 1, 0, 1. And so if you get them like 0, 0, 0, 0, 0, 1, 0, 0, 1, so they're all going to be off all the time. So this is 0, this is basically a truth table. You've got 1s all the way down, and then it's all 0s. That's pretty cool. The purpose of the circuit will be to display the binary. Yeah, well, you think? Jesus. I mean, it's to display which of the value it is as a binary, you know, if x, okay, x0 to x1 represent a 3-bit binary digit, with x0 being the least significant bit and x2 being the most significant bit, so in that order, x2, x1, x0, and then q is which of the actual, gives like 8 possibilities, and the 8 binary numbers that can be represented across those 3 lines of signal will then be kind of selected. Tell which binary number it is. Yeah, yeah, thank you. And then, figure 2 provides an output S that is equivalent to one of the outputs of logic circuit figure 0. Which one it is? It is. There's a not of the end of the end of the end. So like they need to, oh, no, that's an or. Wait, what? Yes, but this is relying for you to apply De Morgan's theorem, or recognize this as De Morgan's theorem. This is all of them true, because this is not, no, wait. Yeah, not this or that will become not this. So not, yeah, whatever, but I'm pretty sure that is the last one, Q7, because it's 111, which is 7 in decimal. Yeah, let me just finish that one, and then some functional. Cool, let's do some functional programming in, I should have taken note of the time, I had it. Come on, come on, yes, hello. Let's jump straight to the list, because like, yeah, it's, oh my god, right, let's the basics. Okay, so add, square, and pred. Adds them together, square squares them, and pred is the predecessor, is the one like that comes before. So add examples. The domain, man, there's the domain it goes into. So the domains of pred is the codomain is what it takes you to. I suppose you can't have the pred of 0. It depends. I guess it's either n or z. No, so it's z. Okay, so that's the older set of the integers. We're talking about z. So if the domain of z is pred, the codomain is z as well, because it's from infinity minus 1 to plus infinity minus 1, if you will. What is the result of applying? So you're compounding the function. You're taking the square of the pred to argument 3. I'm sorry, argument to the argument 3. So that is the square of the pred of 3, that is the square of 2, that's 4. Add takes 2 argument. Add could be partially applied to argument 4 and 6. So if I have add 4 and 6 is actually, can I? Fine, I'll just do this like that. Yeah, so you're add 4 and 6 here. What time is it when you're doing the functional programming? 33:08 for the FP. Add 4, 6 takes 2 argument, but really what you can define a, how would that work? It's really add 4 to add 6, right? So it's kind of like, you could, if you curry the function, you lock it in, and it's add 4 of 6. So you would first apply, or actually probably the receive first, you would first apply this argument. Partially applying the function means you give it only one of the ends, and it will return a function. So this this is a function that will return a function. So this will take a number and will return a function that itself takes a number that then will return an n, right? I can't remember. This is in Haskell. You have to kind of, if you learn the functional illustrated by Haskell, is that so the partial application is you lock something in. This returns its own function whose arity, that's the number of arguments, arguments arity. You think parity if there's 2, I guess, but like arity has been reduced, and now you've only got 1 argument, and then you sort of apply the second one, and then you can actually return the result. The reason that is useful, and that allows you to mass apply, if you kind of want to use map, you can add 4 to this. This also means that like doing the first one, when you're doing complex things, they can be delegated to different bits of compute, right, kind of CPUs, or even like servers in the data center, because all of this is stateless, and you're passing a function that already contains the data, if you will, and then you're just kind of saying, apply that. So 3 marks there. Let's see how they, I have not got the, I don't have the thing. One approach being distributed in more than one server function. Oh, wait, there we go, right? So like 2 features is that it is stateless, and I suppose testable, or like the statelessnicity means that it can be parallelized because it's not dependent on its previous state. So if I were to apply this across a list, of course, sometimes it will depend on one another, but that would just mean like you need to figure out which function, which sort of like curried function you're going to return to do that. Let's have a look at the list in functional thing. What are the heads and tail? The heads is Blackpool. The head is just Blackpool, kind of as a string. The tail itself is a list that takes Paris, New Brighton, Toronto, or the car and the cooler. What, is that it? Like, are you joking? Fine, and then writing. Wow, okay, so let's have a proper one. There's only like 3 of them on the AQA. I know them all, and I love them all. So this is a way of defining a function recursively, right? This is your base case to say if you get given the empty list, then at 0. Otherwise, you are going to get given a list that contains this is literally Haskell syntax. So this is it's quite practical to use Haskell if you really want to lean into programming. Either you get the empty list, in which case you return 0, otherwise you get a list, you split it into its head, x, and its tail, xs. That's the typical notation. And that becomes x plus, and you call the function again, recursive call to this, which means it basically takes the total, it sums all of the argument. I know, James David Smith, 39, this is getting crazy. So it's 3941 hyphen CS7 kilometers. Oh, CS7 kilometers. Interesting. Yeah, it's like it's such a shame that I'm with you on this. It's underrated, and it's not, I think, because you know, remember, you want, as I was explaining earlier about something else, you also want this to be able to be taught by physics and math teacher. Which is, yeah, I remember like asking a math, so there was, I'm very friendly with a math teacher at school because I've got maths envy, as we've established, and I was reading this kind of excellent little paper called A Tutorial Introduction to the Lambda Calculus, which is the work of Alonzo Church. That was Alan Turing thesis supervisor, and this is like, you know, around the same time. It's kind of things that are ultimately, if you will, if the Turing machine is in procedural, because you're kind of like moving and you're kind of doing the thing and so on, the lambda calculus is the same thing about what problems are computable, but in functional and stateless. And they're kind of working, obviously one is the thesis supervisor or the other, so Church is a bit more established, but I forgot what I was saying. And like the maths teacher didn't know about it. So I guess, you know, maths is broad, is what I'm saying. And so the total function works by all of the numbers of a list. It recursively adds the head of the list with the total applies to the sum of the list until it hits its base case, meaning the list is empty. The tail, so when the one below, when we get down to one element, the head is that one element, and the tail is the empty list. And then we've hit the base case, that becomes a 0, and so we accumulating into that 0 all of the sum of the list. Functional programming such as map and fold, a higher order function is a function that takes function as an input and might even return some functions, although not map and fold in an instance, but like all functions in functional programming, that's why it's the lambda calculus, have an arity of 1, because if you get more than one argument, it becomes something that takes you know, your actual thing, and it will take return a function of that itself might take an actual thing and then return like a number and then return a number like we do for the thing. The result of the application of this fold function, when we're going to fold, that does oh, we don't explain what fold is. Fold is going to take start with this becomes the best case, like the empty list is you start with this, and otherwise you multiply, you reapply the same logic, but instead of like you put 1 in here, a multiply in here, and this is your starting list. So it's going to be 1 times 2 times 3 times 2, that's, and they don't even say show your work or explain, that's 4 times, that's 12, I'm guessing, and yes, I love this one, it's a brilliant one. Is this the one? Yeah, this is the Fahrenheit to Celsius. We love this. So we've got this is, okay, what do we have? We have a list of temperatures. We have a function that looks like it's is giving me FU. FU will return the centigrade based on Celsius. FV will map FU across the list of, will map FU across its argument. Then this is something that does a sum. No. this counts the number of elements in what it's given, right? Because it starts 0 and then for each of the x it adds 1, so that's the number of elements, and this is the sum. This fy is fx, which is the sum, divided by the number of elements in a list C. And finally, fz is fy, which is the average of fv, which is the map of the fu of b, of d, right? And then we're probably going to call fz includes a higher order function in its definition. This is in its definition. This uses fw. This calls fx, which takes no higher order function takes something or returns something. Yeah, map is a higher order function. It's using the definition, so that would be fv. Listed function is a recursion is definition. Those are those two, because you can see they all need 2 lines because you need one for the base case. And then the result, well, fu50, there's going to be 50 in Fahrenheit. Fv temps is going to give us like all of this converted to Celsius. I'm guessing, are you allowed the calculator here? Calculate the result. I mean, have they given you something that are easy to do, where like minus 32, 5. How would you... Manti-Sen exponent questions, I would rather not, because I'm really not good at it. Because yeah, I'm not. Frankly, I could have a quick look, but I'm not going to be very good. I'm much more comfortable with this. So fv temps, sorry, fv is mapping this, right? So fv temps is going to return this list in Celsius. I wouldn't like. Why would you? I hope you have the calculator if you need to convert this. Because you don't have a computer in this one. Fw temps is the number of temperatures, so it's going to return 4. Fz temps, no, Fz temps is the average, but we're calling, there's a point where we call Fv, right? Like it's the, yeah, right? So we kind of first convert it and then take the average. So it's going to be the average of the temperatures in Celsius. And that's the average of the temperatures in Celsius. Converts them in Celsius and then works out the average. In this purpose, the definition of the function fz is changed to fz is fu f, an improvement of the definition of fz, because fzd fy fv was here was fzd is fu fyd. Fu is the count of the fy. Okay, what? We want to change fz to fz, so like proposed, okay. I'm gonna have to have, they have both in front of me because I'm just like not sure. How does that improve it exactly? Well, oh yeah, okay, that's good news. You have the, yeah, I don't know. Or you can pitch like easier question and yeah, I guess binary. Fair enough. Well, that's good news then. This is more the kind of question that's interesting. So fz was fy of fv, which is the average of the converted to Fahrenheit, right? Kind of like the mapped converted to Fahrenheit. Was here's fy of d. Oh yes, okay. So here this would first get the average and then take fu, which is the unique conversion, to do the conversion once. And in as much as like this is a bit mouthy, whereas here you go, I mean, like in terms of like I mean, you might kind of lose an n, but because there's a factor, I think you might reduce the. I don't know. You're not expected to give an answer in terms of computational complexity. But what you can simply say is that instead of like converting each of the values and then taking the average, is going to take the average and then convert that to Fahrenheit, which feels like just as you explain it in English. You don't have to, it might be the same order. That's why the big O stands for. But like clearly that's less computations, right? That's kind of fewer calculations. Okay, and then big data, yeah, no, fine, we've done this before. Okay, right. So binary, I don't want to be doing this, but I guess I'm gone star. Okay, so this is in fundamental of data representation. Number system, binary number system. That would be that one, right? Kind of no, pre-2019. I mean, like, what do we? Yeah, I wonder. We want the kind of like lowball grade inflations, kids these days, the exam back in my day was the real high level, now they put the grade boundary of DA at 45, which I'm barely exaggerating for comedic effect. I'm not going to do this. A Mantisan exponent, unsigned fixed point, unsigned, that's better. At least we're not messing around this. Okay, the binary number into decimals, that's cool. I can do this. So we have unsigned fixed, I can scratch this. Right, at 4507, this is floating point. Okay, unsigned float, that is 10011. That's the Montesa, and the exponent is 10001. So you can express this as a clear, so this is floating point, right? So what this means is that this is 1 comma this, right? To the power of this in binary. Where's my power? It's my caret above 6, as it always is, right? So you know that this number here looks suspiciously like 16, right? This is 16, this is 17, right? So this 17 in decimal. Okay, no, fair enough. No, 17. I don't know why I'm kind of worrying about this. So you want to shift, you're going to need to shift. Ooh, unsigned. Oh, fixed point. Sorry, fixed point binary. What was the one of fixed point binary number? Oh, sorry, after the binary point, I'm just kind of like completely tripping myself out. So this is, sorry, we're now looking at this. Fixed point binary, that's like, yeah, whatever. This is like something. The binary number into decimal, I guess I'm going to multiply it by... so you know it's kind of like this number. So let's put it back without the decimal point. This is how I would do it. I don't know if this is the method they recommend. So whatever, and then it's divided by, because in order to do this, I've had to multiply it by a bunch, divided by 2 to the power 17 or 17. No, yeah, divided by 2 to the power 17, I guess. So if you, as you move like the comma, like the point, that's a point. So they're annoyingly they're commas in French and points between like the big thousands, whereas like in English notation it's different, the other way around. So this decimal point here, you can move it to you would have to move it to the right once, multiplied by 2 for. Oh no, so it's not 16, it's kind of like, yeah, okay. Let's do it again. Like to get from here to here, I would need to multiply by 2, 4, 8, 16, 32, right? So divided by 32. Let me not just think any old garbage. And then this, the places, this is 1, plus this is, I want to say 16, right? 16 plus 32 plus 64, not, don't have 1, 2, 8, don't have 2, 5, 6, but I have 5, 12. So, calculator. $512 plus 64 plus 32 plus 16 plus 1. 625 divided by 32. Well, you get your calculator and then you divide that by... Oh... 625 divided by 32, and that is 19... 53125, I guess. So where were we here? Oh, how did I open... Why am I in this place? Because I thought, could I not go back? Oh yeah, okay, I want this one, right? Binary number system QP, no, MS. And this was question 2. Yeah, 1953 because like, or 17, oh yeah, 1730 seconds. Yeah, this is why I had 1730 second kind of like running. Thank you for the Melon Man, although not the Melon Man because it's the Melon Man _1. Maybe there was already, sometimes there's a number 0 in front of you when you want the name. All right, yes. Aha. Oh no, this is fine. 2's complement with that. So, well, you just subtracted, right? You would have to flip this one to its negative into its complement and then add them. And this is as if by miracle. Explain how unsigned, I don't care about this. We wanted some mantissa exponent. I mean, this is unsigned as well. Well, this is okay. The other way around. That's kind of slightly more interesting. So we're starting from like 6, 3, 4, 6, 3, 4, 3, 7, 3, 4, 3, 7, 5. I'm less sure about this, if I'm super honest. I mean, this is 6, 3. I don't know. I gotta say, I'm not sure how you go backwards. Like the other way back from decimal to binary. I mean, would you sort of tempted to do the same thing? But I wouldn't know how to even. Oh no. So this, okay. So I've got 3, like the maximum I can store in here, and is that not helpful? No, it's not helpful. The maximum I can represent here would be like, that's 31, right? Because there's a 16 in there like that. So do I divide it by 31 or like do okay, I genuinely don't know. I've got a egg on my face here. And we're not even talking floating point, this is all fixed point. Is that what I'm looking at? Like, sorry, this is 3-1? No, 3-2, okay. Oh, well, that's super helpful. I would like, before the decimal point, it will be 4-2-1. I'm not kind of being helped here. I mean, there's absolutely no, the steps are. I mean, in fairness, it makes you can just get like, you can get the 2 as long as you get it. If you get the calculator allowed, you probably kind of a program to do this. It's not, from the most significant to least significant, if they add up to less than number you won't then take it as 1, 4 fits, 2 fits. All right, okay, that's fair enough. Yeah, 4 2 1s, and then that becomes your 1. So I would make that like, yeah, so that's why it's kind of a that's 7, that's a 6. Yeah. Okay, so that's 6, and then you've got whatever. All right, it's kind of literally that you do it bit by bit. That's fair enough. Yeah. This is the 6, 1 1 1 0, and this I guess is whatever's left, right? That's like, that looks like 1 plus 2. That's 3. Plus, not 4, but then 8 plus 11. I guess 6 and then 11. So it's like 6 multiplied by 11 and. All right, and then you do this is kind of a divide. Yeah, so it's just kind of like the number of places, except that's a half, right? So like just like this is 1, yeah, 6. That's 4, that's 2, that's 1. So I'm getting James van der Vink is kind of explaining to me how to do the thing. I hope like you guys in the chat are getting it. You can follow the chat. What it means here, right, is that I know that those like slots here take the number places, just like we know in kind of non-decimal integer binary, I suppose, right? This is 1, this is 2, this is 4. Those are your name places. So this is 1/2, this is 1/4, this is 1/8, this is 1/16, and this is 1/32. And so we need to express all of this bullshit. And so there's the 6. So kind of like, that's my integer part. You can't, it's not all half, but it is a quarter. So I know this first one's going to be a 0. So I've got like already my 110 dot. It's not, the half is not there, right? I don't have enough for a half, but I do have enough for a quarter. So I take the quarter, that's like 0.25 taken off. So subtracted from this, there's like 1.25. Oh shit, 25. So like it's like I'm getting this kind of left, 475. And then yeah, and then you gotta know your, I suppose like if you work it in kind of like halves and stuff, but like then it's like after that it's kind of 0.125, which doesn't fit, that's a 0, and it's like 0.0 whatever another half of this is. Okay, so like powers of 2 are easy, I know them by heart, like halves of like, you know, 25, 125. Yeah, 006. Yeah, so that fits once. So there's 0 and then 1. Right? And then subtract this from... Yeah, I guess if I had the calculator, right, I could say like, okay, so like put this in the... right, like let's just copy this. Reset. And then like 0.009 476 minus whatever I got there. That's this. And then I got like this again. Oops. Yeah, I'm like super bored of this already. And then the next one after that is like the next half. So it went into 1. I've got the remainder, and I need like 1, 2, 3, 4, and like probably 1. I mean, I guess, and like the rest, yeah, the rest is at least like thing. And like we've lost some stuff here, right? Because in terms of precision versus the binary one, the decimal one, I want to say, because so that's like half, quarters, eighths, 125, 16th. 32nd, so 1 divide 2, half, quarter, 8th, 16th, 32nd. Yeah, we've kind of like got a spare, whatever that is, right? We get a little bit spare towards the end. It's not quite exactly at that, but it does fit at least once. And so that's kind of good enough for us. This would have left a reminder, so they're probably kind of like more bits after that. And on that note, yeah, well done, James David Smith. Like sometimes you get a school, you know, like all teachers say, sometimes I think they teach me, and in that instance that was true. This is not the floating point one, because this has always... Two's complement, I'm happy, but like the floating point, I just have not practiced it enough because it's all the math stuff. So really, a bit of a different animal, that paper 2, right? Because like you've got the stuff you need to know, and you get the stuff you need to know how to work out. So knowing the sort of algorithms and mechanism can allow you to get those like functional programming and binary question, if that's more your thing. But you can also rely, this is not something you can cram at the last minute, whereas all of the book knowledge, which is, you know, we've done a, I mean, it's worth checking out like a full paper to see kind of roughly how that's distributed. All the book knowledge, you can revise this with flashcards. And on that note, I'm going to go and have some, oh, hello. Yay! Right, the component is the digital analog converter. This is knowledge. This is checksum, ciphertext. Oh, hello. Yeah, there's a bunch of good stuff on there. Fetch executes. Oh, a 12er on the fetch decode execute. Fetch execute. Missing something there. Actually, it's missing, even the fetch decode execute is also missing checking the interrupt register. So it's good to, like this one is good to memorize as a sequence, because it is a sequence, like from Chrome, send counter, current instruction register. Remember, like nothing goes straight into your CIR or your PC. They have to go via the MDR and MAR. But again, this is like all express the knowledge, a description of what happens, but, oh, okay, and how the hardware of the computer could be improved so that program can be executed more quickly. So this is per core, that fetch decode execute. Of course, you can, if you can parallelize the execution of instruction and by multi-core. I don't know if pipelining is on the spec for AQA, but you could kind of like pre-fetch, right? Kind of like just fetch the next one as you're decoding the current one. The problem with pipelining is that you may have I don't think I'm going to be doing a stream tomorrow, James. I'm going to be very honest, because I need to leave my home at about like 5:30 anyway. So if I do a stream, it would probably clash with whatever maths you may have, because it's going to be at like 4:30. So I might as well record a video in the morning, right? Because it's kind of about as interactive. So this is the last time we'll ever speak to each other again. Fetch decode execute, yeah, another way to improving is pipelining, but I'm not sure this is on the spec. It's definitely on OCR, the proposed interrupts. If some like a piece of hardware, it's never the user, like the user might be kind of doing Control-C or Control-Alt-Delete, that's the keyboard is sending an interrupt. Needs some processor time, and depending on like very priorities, is to interrupt the current execution of what's going on. Whatever, you get the vectored interrupts thing. Oh, hello. Oh, hello. Yeah, this is DB. I'm sending. Yes, here we go. I'm smelling it like a thing. This looks a little bit. Yeah, here you've got your seat number, screen number, because it cross references it. Actually, they shouldn't be underlined together, right? This is its primary key and it refers to this. This is less complex as this was 23, less complex than the DB questions we've done on yesterday's stream. This combination arises in database according to told. Get for whoa. I'll pass. So this one is going to be the one I don't. Yeah, crowd and rest. RESTful application. Yeah, there's a vague translation of like your URL into actual commands. I didn't care about it when I was a dev. I didn't still care about it when I was a teacher. I'm sorry. Oh, Jason. Reason one is he was the leader of the Argonauts, and reason two is he got the Golden Fleece. Okay, XML is garbage. The problem with XML is you do never know whether the data is meant to be like as the content of a node or as an attribute. And an XML also needs a grammar somewhere, right? Kind of like what are the expected, because you need to be able to parse it, like the expected tags and like where are things going to be in attribute. So this is why the XML, pure XML is the thing. You always create your dialect of XML, like HTML is a dialect of XML. JSON, it's basically a Python dictionary. Right, in that like it's subjected to the same constraints. You've got keys and then values, and those values can themselves be lists or can themselves be like sub dictionaries, key value pair. So here's the key, has got one value which is a list, but it's got itself like a whole bunch of kind of key value pairs in there. So less ambiguous and probably kind of leaner as well in terms of like the number, like the total number of characters you need to send over. Because it's between the server, right? Kind of it's about like between the server and the booking application, so that's over the wire. That would probably be a good one. Hello, this is the one I'm not going to be doing, especially not for 2 mark. Oh, they show you where the dot is. LCR doesn't show where the dot is. Actually, I can probably hack this one, right? So like this is, the exponent is 1, 5, and I used to know this. I used to be able to recognize like bytes, like the top of my head. Sorry, this is 8, 4, 12. Sorry, this is your left to right for me. This is 12, this is 13, right? So like your well, this is 13. You're going to move it by 13? No. I actually, this is going to be less, as they say in maths thing. Yeah, you can stay. I mean, I know that this is like probably where we kind of think. James, you can say subscribe to my channel because I hope to be posting some stuff about my research on AI in higher education. As of course next year you most likely be part of higher education. I'm always interested to kind of see what the actual students are going, and maybe they could find out something about it. I'm not sure I can kind of hack this one if I'm being super honest. And then okay, and then we need to normalize and normalize. That's why I don't like this, because the normalization is kind of slightly beyond me. Ooh, a calculation is performed in relation so close to 0, number of stories 0. This is an underflow. Too large to fit number of bits. It's an overflow. Represented a value. It's kind of a rounding error because of floating point. Ooh, because in 6.1 and 6.2 they're not normalized, I'm guessing, right? This is going to be the problem, right? Because there's a 0 here, right? So like immediately you could like chuck it, you get yourself one more bit of resolution where you're assuming it's a 1. You're not really interested in a 0. It's like 1 point something. So that would be the 6.2. I don't know. Well, 6.2 because you've moved it. Oh, the normalized floating point. I don't know then, because I don't know how you would. Oh, sorry, with 8-bit multi-sign 4-bit exponent as opposed to. Oh, sorry, they're using 2's complement. That's my bad then. So in that case, all bets are off as well. So this was a minus something, yeah. And then I suppose, so if you do them as unsigned, of the unsigned floats, we view twice as many floats because you don't have to cover the negative numbers. And evidently, so the mantissa, I guess the exponent still needs to be signed, so you get the resolution of going minus minus. But if you're not bothering about negative numbers in the mantissa, yeah, so it was already normalized with a 0. That was because it's 2's complement. It starts with a 0 because there's no negative component to it. Anyway, thank you so much for watching this. It's going to be the end of the series. but maybe on results day. I don't know. I'm less interested as to what's actually on the paper than I am for the paper 1 because of the prediction for section D. Oh no, even drunken my chocolate. Yeah. Anyway, thank you very much for watching, and break a leg on paper 2. Remember your training, and ultimately, it's your mark is only a reflection of how well you did on that one particular day. So like all of your, all of the judgment, the academic judgment on you as a computer scientist is based on 2 times 250 minutes and 2 hours and a half. And this, of course, you get extra time. So don't